So first, Ms. Eamon Conjo, professor at Imperial College London. Remotely, we have Mrs. Virginie Fraisse, associate professor HDR at Jean Monnet University. Virginie, can you hear us correctly?
Yes, it's okay. Thanks. Hello.
We have also Andrea Pina, professor at Leipzig Sorbonne University. Remotely, we have Michele Magno, Profit and Senior Scientist at ETH Zurich. Michele, can you hear us also correctly?
Yeah, very well. And hello, everybody.
Perfect. And so myself, Mathieu Azer, I'm professor at IMT Atlantic. And so the supervisors are Daniel Ménard, professor at INSAREN, and Glenn Heroux, research engineer at INSAREN also. So, Mr. Christophe El Zeinaty, the floor is yours for 45 minutes, and afterwards we will have a second phase with the questions and answers.
Yes, thank you, Mr. President, for this presentation, and I want to thank the member of the jury as well, and everyone for coming. So I'll be presenting today my thesis work on generative AI for designing efficient and explainable TinyML models. In this presentation, first I'll start by introducing the context of the thesis and the challenges to deploying models on microcontrollers, and also the main objectives. In the second phase, I'll be starting to go into some details on object detection and optimization, so we can know some notion that we'll be using in the core part of the presentation, which is the thesis contribution, where I will introduce the DiceTrack platform. It's an industrial use case that we worked on, and a proposed TinyML framework as well. And finally, I'll conclude our work and share with you some short-term and long-term perspectives. So let's begin. To give a global context, nowadays computer vision applications in terms of market growth are increasing from year to year, with a perspective of $72 billion by the year 2031. At the same time, we can see also the number of the devices, IoT devices, are increasing as well, with a perspective of 150 billion devices by 2030. This type of growth has influenced the adoption of AI everywhere in our lives, from autonomous driving, drones, smart farming, and smart glasses as well. And this widespread of adoption has led to a key challenge: where and how to compute. That's why we have cloud AI that has its own limitation in terms of bandwidth, latency, and energy consumption. And that's why it's important to explore AI on the edge to try and solve these type of problems. In this thesis, we focused on the object detection task. So what is object detection? Object detection is simply the task where we want to first localize the object in the image, having their precise location, and in the second time, it's to identify them. So as you can see here in the picture, we have 3 objects, and each one assigned to its own object class. These type of algorithms are usually heavy in terms of computation and calculation. That's why it's challenging to optimize them and to deploy them in a restrained environment. I want to share with you the main challenges in TinyML application, which are the deployment bottlenecks. So as you can see here, cloud AI virtually has infinite memory in terms of RAM and flash. If we go to mobile AI, it's much more less, but still we can see gigabytes of RAMs and gigabytes of flash, so we still have some flexibilities. The real challenge is in terms of tiny AI, where microcontroller can have approximately some kilobytes of RAM, SRAM, and some megabytes, few megabytes of flash as well, which make it critical to find ways to optimize object detection models. In my thesis, we had 2 main objectives. At first, we wanted to bridge the gap between foundational research and practical deployment. In the second time, we want as well to be able to enable efficient and accurate real-time deep learning models on microcontrollers. Now, knowing the context, I want to walk you through some notion that we need to understand, starting with a small history on object detection. So object detection started with the pioneering algorithm of Viola Jones in 21. And these were considered traditional methods, if you want, until the rise of deep learning methods. With deep learning, we have many types of architectures that exist and continue on evolving from year to year, from one-stage detector, anchor-free detector, two-stage, and most recently, researchers are refocusing on transformer-based methods as well. In this thesis, at first, we will focus on deep learning method, specifically based on convolutional neural networks. So this is a typical general form of the pipeline of object detection, starting first with the backbone part. The backbone part is responsible of extracting features from the image from different layers. Then we have the neck module, which is responsible of fusioning, if you want, merging these pixels from different layers to be able to highlight the most important pixel, if you want, in an image to be able to do the predictions. And finally, we have the head network where the model will do the prediction, finding the coordinate of the bounding boxes, as you can see in this image, and also identifying the objects. Knowing that, let's go to the part on how we can evaluate these models. So the main metric in object detection evaluation is the mean average precision. Here I put at threshold. You will understand in a few seconds what I mean about it. But first we need to understand some concept to understand all the steps of this calculation. So we start with the confusion matrix, which is well known in deep learning in general, and it's a way to interpret your results. With this confusion matrix, there is a IOU. And here it comes the term of the threshold. First of all, based on our application, we'll set a certain threshold, let's say 50%. And once we have the predicted bounding boxes, we want to compute the area of intersection between the ground truth annotation and our predicted bounding box. If this area of intersection is greater than the threshold we set to 50, we can consider in our confusion matrix that this is a true positive object. If it's less than the threshold, we will consider it as false positive in this case, or even though if it respects the boundaries but the class was misidentified, it's also false positive. As for false negative, it's when we have an object in the image, but the algorithm failed to predict anything for it. In terms of true negative, in object detection, we don't really take into account this metric because it represents simply the background. And we don't want to evaluate our detection model if it can detect the background or not. Now, knowing that, we can compute the precision, which is an important metric, and it simply answers the question from all the predicted bounding boxes, how many the algorithm truly predicted. And it's a ratio between 0 and 1, 1 being the best. And finally, we have the recall. It answers another question that can complement the first one, which is from all the ground truth object that we have in our test data set, how many we are able to find. And ideally, in object detection, we want high precision and higher recall, but we can also try to find a compromise between the two based on our use case. Now that we understand all of this, let me walk you through how we can compute the mean average precision. So here in this graph, we consider that we took a class, let's say cat, and we sort bounding boxes that we predicted based on confidence, and we plot for this class the precision and recall curve. As you can see here, the precision can go down, then up, while the recall is increasing. And this is simply because imagine each time we have a new object in the image, the algorithm can either detect it as true positive or as a false positive, which can either increase the precision or decrease it. And for the recall, it will stay either consistent or it will increase. It cannot decrease. And having this form of curve will not allow us, if you want, to compute the area under a curve in a fair way. That's why we need at first to interpolate our precision to have a monotonic curve that is descending. And this is simply we will take the precision, the maximum precision at each record level while looking always onward. Then, once we have this new curve, we can now compute the numerical integration under this curve based on 11 spaced, evenly spaced points. And this will give us the average precision of this class that I said cat in the beginning. So let's say cat. Now this process is repeated if we have multiple objects. So we will compute for all objects with this same threshold the precision of the average precision for each object and each object class. And finally, we compute the mean average precision to know the overall performance of the detector. Another important aspect is efficiency evaluation. We have target independent and target dependent categories. At first, for target independent, it's like flops and max for computational complexity. For target dependent, we have memory usage in terms of flash and SRAM. And we have two important metrics for real-time application, which are energy consumption and runtime. These two metrics are correlated. So if we have, normally, if we have a faster runtime, we will have a more efficient model in terms of energy consumption. As in terms of data sets, in object detection, there are two main data sets that are used, the Pascal VOC and the MS COCO. The main difference, they have similar kind of images that are annotated with bounding boxes, and the main difference is in the number of classes. So Pascal VOC work with 20, and COCO was 80. And most importantly, it's the evaluation metrics. So with Pascal VOC, it's more relaxed. We take a threshold of 50. And for the MS COCO, we take a threshold of going from 50 to 95. And in TinyML application, usually most of people focus on benchmarking and Pascal VOC because it's more flexible in terms, more relaxed in terms of metrics, evaluation metrics, and usually it's enough as a general purpose data set. I want to show you some of the state-of-the-art models for object detection on Pascal VOC. In this graph, you can see we want always to have a higher mean average precision and lower computation, having the third dimension, which is the model size. So ideally, we want to optimize these three metrics based on our application. So not always that the best mean average precision is the best, because if your application can accept lower mean average precision on a general purpose data set, it can work well on your data set. And in this way, you would leverage less MAC and smaller model size. Now that we know these terms, I want to introduce what are people doing and what we did in terms of optimization techniques. This is less common, but it's still feasible, the traditional learning-based method. So you can have normal image processing techniques with classical ML, and you could have good results for your application. It's less used nowadays, but it's still a possibility. On the other hand, most of the research is on the deep learning field. And in this, we have many categories of optimization. At first, simply if you know how to handcraft your own model design, you will be able to design a lightweight model. Then we have the category of parameter quantization, which consists of quantization, meaning you have your weights represented with floating point 32 bits, and you want to represent them in a smaller precision. It could be int 8 or even go to binary weight as well, and this will reduce the memory footprint. The parameter removal, we have pruning, and it's a technique where you will look at your architecture and try to see redundancy and connections and try to remove them in a way without affecting your accuracy. And it also helps in inference speed and in terms of memory footprint. And finally, we have parameter search advanced technique based on neural architecture search and neurogestiation. Neural architecture search, it's a way to automate the way you design your model based on your hardware constraint. And neurogestiation, it's a way to transfer knowledge from a bigger teacher to a smaller model to improve accuracy without increasing the model size. In my thesis, we focus on handcrafted design, parameter quantization, binarization, and int 8, and finally, a combination of neural architecture search and neurogestiation. And this led to many contributions. I will list them in from the most recent one. So recently we had a paper accepted in a journal, ACM Computing, and it was a comprehensive survey on practical and theoretical aspect of object detection, particularly in TinyML for the object detection pipeline. Also, we published at IJCNN, it's our fully open source framework, generative AI framework to propose new TinyML models using LLM. And as well, we introduced the DiceTrack platform, our industrial use case at ICASP, where we did some optimization on. In this talk, I'll be focusing on the LLM guidedness framework and the DiceTrack platform, with also some insights from our survey as well. Let's go to the thesis contribution. So I'll start with the industrial use case, the DiceTrack platform. So to put things in context, it's a work we did with a startup, and they have a goal creating a hybrid board game between digital and physical content as well. So my work was based on the DiceTrack platform. It's a device where you can throw dice on it, and we want to detect them and classify them to be able to use them in a game on another board console. And you have images based on the DiceTrack. Since we have two cameras, we have images like the input image here, where you can see the dice face and the adjacent part as well. And that's why we need detection, because we want to detect the valid faces. Then we want to classify them, as you can see in the images in the middle. In this part of the talk, I focus on the classification. It was the easiest way to start my PhD in optimizing deep learning model in a classification task. And we have an objective by the end of this presentation, we have the fully completed pipeline. So let's start with classification with hardware constraint. We have an ESP32 with two cameras. As memory limitation, we have 4 megabytes and 520 kilobytes of SRAM. You can tell me 4 megabytes, it's a lot for TinyML application, but here we should keep in mind that this is an application that interacts with Bluetooth module, Wi-Fi, and so many aspects other than the deep learning models. That's why we need to optimize them as much as possible in terms of memory footprint. So what are the contributions of this part? We proposed a new DiceVision dataset for detection and for classification. We attempted to optimize a off-the-shelf deep learning model, MobileNet V2, using quantization. And we proposed two ultra-lightweight models based on quantification and binarization. First of all, I want to describe a little bit the dataset we used. So this is a dataset that we annotated using first. We took the picture using the DiceTrack platform. Then we needed to find the way how to annotate the bounding box manually. So the strategy was to take the valid faces in the green bounding boxes here. You can see all the pixels alone, isolate them if you want as a valid face with their class. And for the adjacent part, we took a small part of the valid face and the adjacent part. In this way, the model will learn how to differentiate between these two faces. And this was used using an annotation tool. It's open source, Label Studio. As I said, for this part, we focus on the subset, which is the DiceVision classification part. It's simply, we crop the valid faces from the main dataset. And these are the images that we will be used to, so the model can learn and converges. We resize them to 112 by 112, and we applied some augmentation technique to take into consideration some lighting and different scenarios that we can face in real-time cases. So let's start with the first part, which is optimizing MobileNet. So MobileNet, it's well known as a lightweight deep learning model for mobile and edge AI devices. It's well known because of its use of lightweight depth-wise convolution that reduces the number of parameters per layer. And the typical floating-point model of MobileNet, 32 bits, it's approximately 9 megabytes. So at first, we attempted to apply post-training quantization for 8 bits. Then we used quantization-aware training for 8-bit quantization and sub-8-bit quantization for weights and activations. So as a first look, you can see here, compared to the floating-point model, for post-training quantization, it didn't work really well. The accuracy dropped a lot. So we did a small exploration, and we saw, we confirmed, if you want, that the depth-wise convolution are really sensitive for quantization. That's why taking into consideration the quantization error, it's important. So the QAT model, it's much more better in terms of accuracy. We attempted to go further for int4 and int2. And we have accuracy drop for N4 still acceptable, but for N2 it's not random, but it's not acceptable anymore. At this point, we decided to focus on-chip memory deployment. We don't want to restore to encoding and decoding technique. That's why we focus on the Int8 mobile net. So as you can see, it can fit into the flash of the ASP32, but it takes more than 50% of the memory only by using the deep learning model. That's why we wanted to propose two new models in an incremental way adapted to our use case. Starting with SQLnet, it is inspired by MobileNet v2. It has less layers. We use depth-wise convolution to reduce parameter count. In terms of filter, we set them between 16 and 64 to always capture high and low dimensional features. And one important aspect was to fixing the kernel to 3 by 3. In this way, we limit the memory augmentation to a factor of 9, compared, for example, 5 by 5 that can go up to 25 and so on. And last important aspect is replacing the flattened layer between the CNN and the fully connected layer with a global average pooling. And this helps us to reduce the parameter count to 0 to this layer, and as well create an independency from the input size. This model also was quantized during the training to Int8 activation and weights. Now we wanted to test if we can go further with binarized neural network. So we took the same architecture design, followed the same strategies for filter, kernel size, and global average pooling. What changed here is due to the depth-wise convolution that are sensitive for quantization. Since we are aggressively quantizing, we decided to go back to normal convolution, which will take more parameter, but we can quantize more aggressively. And the last important part is applying the straight-through estimation technique. Since we have now activation and weights between -1 and 1, our gradient aren't differentiable anymore in the backward pass. So the model could not learn. Straight-through estimation technique help us estimate our gradient, so the model can converge and learn when we apply the backward pass. Now let's go to the results. For the experimental setup for training, we used an open source framework called LARP. It's used for optimizing the inference and training for binarized neural network. For the net, we used activation and weights of -1 and 1. SQLnet Int8 based Int8 for also activation and weights. As for inference, we target three target if you want, the SP32, Raspberry Pi, and an Intel CPU. For baseline, we have one for the accuracy and another one for the model size, and they are based on MobileNet, what we did in the beginning. So let's start comparing a little bit the result in terms of accuracy and model size. As you can see, our proposed methods for our specific use case outperform the Int8 model and have approximately same accuracy of the floating point, when using only 11,000 parameter and 36,000 parameter. And this led to a huge reduction in model size from the baseline. We have the SQLnet, which is 83 times smaller than the baseline. And more impressively, the BANnet, it's 125 times smaller than the baseline model. Now, let's look more into the inference results. So we tested on the SP32. As you can see, with SQLnet, we were able to have a model that is approximately 8 times faster than the baseline. Here, unfortunately, we couldn't test the BANnet on ASP32 because it's not ARM-based architecture. And the LARP framework is only optimizes operation for ARM architecture. And that's why we tested on the Raspberry Pi to see the benefits of binarized neural networks. For the SQLnet, also, we have the same pattern, a model 3 times faster than the baseline. And here, what is impressive, it's the BANnet is 2 times faster than our proposed method and approximately 6 times faster than the baseline. For the CPU, same strategy here as well, and same pattern. We have a model that is 4 times faster than the Intel CPU. To conclude this part, we were able to propose 2 new models in an incremental way for our use case. They significantly reduce the model size compared to off-the-shelf models. And their size, it's interesting because since they are few kilobytes, you can deploy them even on the SRAM alone, which will lead to higher inference time, and this will reduce energy consumption. And as a main insight here, we can say that If you have a specific use case, you don't need to always take a model off the shelf and try to optimize it a lot if you know how to propose a model and how to optimize it for your specific use case. Now, what we want to do is to complete our main objective and proposing the full pipeline of object detection for our use case. An important part of the pipeline of object detection is the backbone, because usually you need always a pre-trained backbone that is optimized to extract your features. In this way, you will be able to detect better bounding boxes and identify objects. In my work, we focused on optimizing the backbone part. We found, based on the classification tasks, that even for simpler tasks, manual design can sometimes take a lot of time, and it makes it harder if we have dozens of architectural choices and hardware trade-offs. That's why we wanted to look in an optimized way, hardware awareness framework, to be precise, to be able to propose a new optimized backbone and to include them in a fully object detection pipeline. In this way, we will be able to achieve our main goal. And this leads to going to the last part. And in this part, we proposed a new fully open source framework. It's based on LLM, and you can train and deploy your model based on your specific use case. So as I said, we wanted to automate the design. So let's look on how we can do it using neural architecture search. So in NAS, you have at first your search space. It can contain configuration of your convolutions, kernel size, number of layers, and so on. You'll have your own search strategy, which will exploit the search space to propose candidates. Each candidate will train it and evaluate it, then use the performance as a feedback to our search strategy, so we can propose another model, and in this way, after certain iteration, the algorithm will converge to ideally to an optimal solution. Based on the thorough state of the art that we looked into in our survey, we found some limitations in neural architecture search, and specifically in the search strategy part. That's why we wanted to focus on this part and try to optimize this phase of the process. So what kind of limitations do we have? NAS sometimes can take up to weeks of GPU computation to find a solution. If you find, then maybe you won't find it. Also, it can be stuck sometimes in some substructures in local minima. And this leads to more training time, and you will not have a perfect solution. And most importantly, it lacks explainability. Okay, we can understand why the algorithm is converging. That's true. But in terms of why did we choose these specific design choices, this is missing in this part. We won't know why the algorithm chose this kind of convolution, why this size, how many layers, and so on. That's why we wanted to see a new way to be able to fix, if you want, these problems. And in these years, we saw a rise in large language models, and we saw that they are capable in many, many aspects, like even in treating data in terms of voice, text, messages, and so on. And also in other terms of application, like question answering, it can go to image captioning, even sentiment analysis, and so on. So we wanted to see how we can leverage such a tool to be able to propose a new models that are optimized for our specific hardware. And with this rise, as you can see from week to week, we have new models. And it's between two schools, if you want, the open source and closed source, with each its own advantages and disadvantages. As for open source, people can reproduce your result, can test faster. Closed source, it can be pricey sometimes. And also, people won't ideally be able to reproduce your result if they don't have access to these models. That's why we wanted to focus on open source in our framework. And we have several objectives. At first, we want to provide a new guided mass way using LLMs. This will reduce the search cost, because here we are prompting the LLM. We won't fine-tune it for the specific task. In the second phase, in our pipeline, we want to have knowledge distillation part, to be able to do to improve the candidate's accuracy without increasing the model size. And here we explored vision transformers, because vision transformers they are well known in terms of accuracy and performance. So we want to leverage them in our pipeline to improve the CNN small model. And finally, we want to tackle the explainability part. We want to enhance transparency between the researchers and the model and the proposed method. Now we can leverage the LLM to know why it shows us these kind of configuration in each step. So this is the overview of the method. It's based on 3 phases, with the main one, the search process. We have the fully training phase, and finally the large association module. Before going into details in each aspect, I want to explain to you what the search phase looks like. So it's based on 5 stages. In each stage, the LLM will be able to configure it. You can see here, for example, in stage 1, the LLM can choose how many layers do we want, the type of the convolutional block. It can be depth-wise convolution block or mobile convolution block. It chooses the size of the stride output channel. And it's important to note here that it will do it in one pass. So it knows the global context of all the stages. So it will propose the 5 stages together. And in each stage, the configuration are replicated. So in one stage, you have only the same configuration repeated Li times, but it can be different between stages. So in time of values, what does this look like? For example, the output channel, we have a range from 16 to 160 in terms of size. The convolution block, we have depth-wise convolution and mobile convolution. We have many other configuration, and we have the number of layers, which is important. It can go up, maximum up to 6 layers. And this will lead to an approximate configuration size of 70,000 configuration per stage. Now let me explain the search process. So for this phase, we want to prompt the LLM with a clear prompt, role, and task with a specific constraint. And most importantly, we will test our search space in JSON file in the prompt. The LLM will generate a JSON file of only the configuration of the architecture, and in parallel, an explanation on why it shows us this configuration for this candidate. We introduced a constraint validation module, and this is important because sometimes LLM can hallucinate and give us model outside of our constraint. So we want to set these values based on our target, and if these constraints aren't respected, we reject the candidate directly. We provide a feedback for the LLM so it can propose a better candidate. Once it's validated, we go to a mini-phase training, which is only 30 epoch, to test the potential of the candidate. And we don't want a dominant candidate in terms of accuracy and number of max and number of parameters. So we apply a Pareto optimization formula to have non-dominant candidates. So we'll have a list of Pareto candidates that we will provide as a feedback each iteration to the LLM so he can introduce a new candidate until the process is finished. Now we go to the fully training phase, and here you can select the best candidate you want for your case. And it will go to the fully training phase. We want to see the full potential of the candidate. And simply we'll train it for more time with some specific hyperparameter, here 120 epochs. And this will lead us to the final student model. And in this phase, we want to explore how we can increase more the results without affecting the size of the model. That's why we go to the normalization part where we leverage the vision transformer. And here, the proposed method is as follows. So you see this formula here, we have the alpha parameter. It represents the 2 loss function of the student and the teacher, if you want. And the idea here is we change alpha in a progressive way. So in the beginning of the training, we rely more on the student loss. And by the end, we start relying more on the teacher. And in this way, we won't overwhelm the student model with complex features from the beginning of the training. Now that we have all this process, let's go to the results, starting with the experimental setup. So as I said, we leverage open source LLMs, the Meta family and the Quen family. At the time, it was the most used for specific tasks. It was the instruct model. So we chose the instruct version, and we tried to choose different number of parameters to see how it changed. So we use the 8 billion, 3 billion, and the two families also to see if the method works with different families of LLMs. As for data sets, as I said, we need to optimize first the backbone for the classification package to be pre-trained on this task. We used Cypher 100 dataset. Then we tested for object detection on the Pascal VOC. And finally, we test on our specific use case, which is the dice vision dataset. For training, for each phase, we have a certain hyperparameter for the mini phase, full phase, and knowledge distillation phase. And for the inference, we tested on the H7 microcontroller. It has a limitation of 2 megabytes of flash. In terms of RAM, it contains up to 512 kilobytes, but we enforced the 320 kilobytes for our search method. And we set the median max constraint between 70 and 350 million. As for the evaluation on the baseline, we tested for the backbones ZNet and two variations of MCUNet. For the metrics, we used the accuracy, computational complexity in terms of million max, the layer user in terms of flash and SRAM, and the search cost to compare with the method that used the NAS as well. So let's take a first look to the classification result. So we can see that our proposed models all achieve state-of-the-art accuracy on the Cypher 100 compared to the other models. All of them are higher than 72%, with the leading one 74.5%. And impressively under 100 billion max for all of them. For flash and parameter, in terms of size, this is translated to models that are smaller than 600 kilobytes. And most importantly here, in terms of search cost, comparing to the NAS method of MCUNet, all our models were found under 4 days compared to 12 days for MCUNet. Now let's look on the SRAM usage part. You can see on the figure, all our models respect easily the 512 kilobytes constraint, and as well the 320 kilobytes with the leading LLM only 165 kilobytes. And I want to be precise here, we are using input images of 160 by 160, and that's usually for TinyML not really small. And if you have increased input size, the SRAM will increase as well. So to be able to achieve this result was really impressive. In terms of search, so let's explore a little bit a small equation study on the use of different LLMs. So we can see in total number of candidates and Pareto candidate, the Meta family, they proposed less candidates compared to the Quen family. And so now here we want to say on average, all these candidates does proposing approximately twice more candidates is important in this case. And we can see this here translated to an average accuracy for the mini phase training of the candidates in the list. Approximately all of them, they have similar mean average precision. In terms of max, the Meta are leading, but still not by a large number. And parameter, we follow the same strategy as well. And this translates with the most important metric is the search cost. And here we can say that the 8 billion parameters, it translates in the best model, LaManat Elite, in terms of accuracy and SRAM. The 3B model of Meta, it's the second best in terms of accuracy and SRAM. And we have the Quen that come last, but still much more faster than state-of-the-art that we compared with the MCUNet versions. In terms of knowledge distillation, here I want to show what gain we got. You can see that all the modules we were able to achieve the 1% plus accuracy. And it can be small, but in reality, the last percentages are the hardest to get. That's why the vision transformer part in the knowledge distillation was important and critical in our framework. Before going to the detection part, I want to show you some small efficiency analysis we did. It's based on this formula and using the tool of ST, which is the PCC tool. We set the voltage is set to 3 volts, and the current draw, we took it from the tool. And the time is expressed in seconds. In terms of performance, we tested 2 types of configuration, 280 clock and 400 megahertz clock. you can see here that the Llama core was the best in terms of speed, FPS, and energy consumption in the two configuration. So we looked into more details into this architecture to compare them to understand why we have this case. And we found out that the Llama core was the only one that doesn't use any attention block. So now we have an optimized backbone and ready to be used in the object detection task. We fixed the Llama Elite. So yes, it's not the best in terms of energy and speed, but it was the best in terms of SRAM and accuracy. And we wanted here to exploit these two metrics in priority. And we fixed the second part of the object detection pipeline by using a YOLO v2, YOLO v3 style to do our test. For the object detection results, so we tested at first on the Pascal POC dataset. So compared to the state-of-the-art model that I showed you in the beginning, we can see that our proposed methods surpassed many of the proposed models, and are really competitive with the best ones. Most importantly here, we can see that if you can manage higher resolution for object detection, like the XENAT model, for example, it uses 460 by 460 image and still manage a good use of the SRAM, you will have better result in terms of mean average precision. So in my thesis, it wasn't the main focus at the beginning. We focused only on the backbone part, and by only optimizing the backbone part, we were able to achieve these results. And these results are translated visually in the images you can see here. So now we have an object detection model that works on general purpose dataset, can detect person, motorbike, and cats, and so on. It can fail sometimes, which is normal. It's a very small model, but generally it performs well. Now having this model, we want to fine tune it on our specific use case and complete our objectives that we set from the beginning. So we took the small version, YOLO v2, with the Llama Elite. As you can see, the SRAM is well optimized, even the number of million max. We tested at first using the Pascal metric 50% of threshold, and you can see for this specific use case, which is easier than having 20 complex objects, the model is able to approximately 100% of the time detect half of the dice easily. That's why we wanted to test the COCO dataset evaluation metric by taking from 50 to 95 threshold and averaging them on all the dataset. And this led to a 77% of mean average precision, which is more than enough for our use case. And just to explain why it's more than enough, if you look at the face dice that we are using from 1 to 6, usually if we can detect 60 to 65% of the dice, we are able to classify if it's 1, 2, 3, or 4, so on, based on the dots. We don't need to detect the whole dice. And having 77% on average detecting this dice, it's more than enough for our use case. And this translates into qualitative result. For the two images, I didn't plot the detection of the adjacent part, but just I want to show you that the model was confident to detect the good faces. And in the last image, you can see it is also confident to detect the adjacent faces as well. Now, to conclude this part, to our knowledge, we are the first to propose a generative AI framework based on guided LLM for TinyML applications with an explainability model and energization phase leveraging vision transformers. This resulted in state-of-the-art results for the accuracy and the memory for the classification part and also detection part. And most importantly, we were able to complete the fully pipeline for the DiceTrack, having an optimized module. Now I want to go to the conclusion and share with you some future works we have. So in the 3 years of my PhD, we were able to publish in a journal a thorough survey on optimization techniques for object detection and specifically benchmarking on microcontrollers. We proposed a new use case, which is the DiceTrack with binarized and quantized models. And finally, an open, fully sourced framework leveraging LLMs and vision transformers with explainability. Now, in terms of future work, in short-term perspective, we believe that the ultimate detector comes from a combination of software algorithmic part and hardware perspective part. That's why if we're able to optimize both sides, we can manage high resolution, which is critical for object detection. And this can be done with also improving the methods on the inference side, because on the thesis we focused on the training and the deep learning side. And this can be translated also by using AI chips on microcontrollers. And as a spoiler alert, I can tell you that the first results on the N6 are really impressive compared to microcontroller without NPUs. In terms of long-term perspectives, we saw a limitation in using transformer-based architecture on microcontroller directly. And this is comprehensible because they are based on attention modules. It can be slow, it can lead to more energy consumption and so on. But it's worth it to start seeing how we can propose maybe hybrid phase or some optimization to be able to leverage their power in terms of performance. And these work started. There are some papers that leverage this for classification tasks. So why not do this for object detection as well? Another long-term perspective, it's leveraging multimodal learning. So let's imagine the framework that we proposed. It's based now on just on images. Why not try to leverage more type of input with all these powerful LLMs or VLMs, for example, use audio, video, and so on in the training phase to be able to improve the results and finally have an optimized model for the detection part on the microcontroller. Thank you for your attention, and if you have any question, I'm happy to answer.
Thanks a lot, Christophe. So just in time, so that's perfect for the time. So